Hello, good afternoon, good evening, good morning. Delete as applicable. That's the beauty of an online conference. So welcome to OO Considered Harmful. And we'll get to that title in just a moment. Just to introduce myself, many of you know me anyway, but I'm Phil Nash, developer advocate at JetBrains for their C++ tools, particularly C-Line. We do have an exhibitor room here, so do come and see us there. In fact, I'm going to do a demo in there right after this, so we won't even have that much time for any socializing immediately afterwards, but we'll talk about that more later. You may also know me as the original author of Catch and Catch 2 test framework, and I'm involved in a number of other things. I won't bore you with the list now. Let's get into the subject. OO considered harmful. Obviously, there's a bit of a play on a meme here. We call it memes these days. They've had different names. Actually, this particular pattern goes back to at least the 40s. Journalists tended to use it in the 40s and 50s, but it crossed over into software development circles, where arguably it became particularly famous in 1968. And we'll get to that in just a moment. But interestingly, this pattern of words, not this particular one, but just in general, using titles like this, that itself has a name, snow clones. This is a snow clone of the considered harmful pattern. And of course, we know it from goto considered harmful. In fact, technically goto statement considered harmful was the title of Edgar Dijkstra's original letter, actually, to the ACM magazine, I believe it was. Now, everybody just about knows this title, but I wonder how many people have actually read it. Now, just before I started, I pasted a link into the chat. So go and get that if you haven't done already. There's a page you can go to that will allow me to ask for some collaborative feedback. Bearing in mind the 10-second delay, I'm just going to drop out of my slides for a second. And you should be stuck on this page at the moment. They're not started, but if I flip it over, hopefully that should have changed for you as well. And I go into present mode so you can see that more clearly. I can see some feedback coming in already. That's great. So as expected, most people haven't read it. Some people may have skimmed it, and there's a few late entries saying they've read it fully. That's good. Quite a few, actually. Surprising number have never heard of it, so that's interesting. I'll leave that running for a moment. We'll come back and have a look how you're getting on in a while. I'm going to carry on with the presentation, but yeah, so as expected, most people have not read it, and if they did, it was probably a while ago. I would recommend reading it again. It's not that long. This screenshot here is about half of the paper. So yeah, you can read it in a sitting. Some of the wording gets a little bit intricate, but it's pretty accessible as well. Now, obviously, here is talking about goto. We're going to be talking about OO today, and other than how the letters slot in, you might be wondering what the connection is. Not just because I wanted to use that title. There's a bit more to it. And in fact, if we look into, he actually says his second remark, the first one is less interesting. He says, my second remark is that our intellectual powers are rather geared to master static relations, and our powers to visualize processes evolving in time are relatively poorly developed. That's interesting phrasing there. So obviously he's talking, we're going to be leading up to how the goto statement plays into this, but carrying on. For that reason, we should do, as wise programmers aware of our limitations, our utmost to shorten the conceptual gap between the static program and the dynamic process, to make the correspondence between the program spread out in text space and the process spread out in time as trivial as possible. So quite a profound statement there, that we should be aware of our limitations, and we want to shorten that conceptual gap between how our programs actually run and how they're written. And he brings in this subject of a dynamic process. Now, as I say, he's talking more about how the instruction pointer moves through your code, and he starts talking about textual indexes in the next couple of paragraphs, which is just a way of saying how we can reason about lines of code in isolation, and how we can take in the whole of our code by thinking about a progression through it. So you can see how go-tos can screw that up. In fact, he does say that even procedures do complicate things, but they can make it manageable. But go-tos make it almost impossible. So we're going to come back to this, but I want to move on because obviously this essay was talking mostly about structured programming. You may see that as maybe a precursor to object-oriented programming. And certainly a lot of what went into structured programming has made it into object-oriented languages. So we haven't lost it all. Or have we? It's a great talk by Kevin Henney, The Forgotten Art of Structured Programming. This was from C++ on C last year. You may have actually seen this. There's a good chance you have, because last time I checked, it had 125,000 views. Now, if you haven't been looking at view counts on talks from C++ conferences, you may be surprised that that's actually a really high number. Most good ones get in like maybe the tens of thousands. There's a few that really break through, like some of Bjarne's keynotes. So for some reason, this got caught up in the upwinds of the YouTube algorithm, and it's doing pretty well. That means a lot of people have seen this talk, which is a good thing. It's a great talk. In fact, I have a bit of a confession here. When I was preparing this material, well, when I was first preparing the abstract, I thought, I know there's one or two Kevin Henney talks that I want to refer to because he's talking about similar stuff. But when I was actually researching, doing the background research, everywhere I went, I just got the feeling that Kevin had got there first with another great talk. And it's a bit like that South Park episode where everything they did, they realized that the Simpsons had already done it. So maybe we could say Kevin Henney already did it. But this is actually good news because we're going to be talking about some quite deep, broad topics. But obviously, in a 60-minute talk, which I have 50 to 55 minutes left, I'm only going to be touching on a lot of these topics lightly. I'm going to weave the narrative to get me to where the point that I wanted to make. So as we touch on some of those things, I can point you to other talks, particularly Kevin's, some others as well, including some of my own. So right on the last slide, I'm going to give you a link to a page on my website with a load of extra resources that you can go and have a look at, including lots of talks. So if I skim a bit lightly on some of this stuff, be reassured that you can do some more research afterwards. So, okay, enough of structured programming. We were talking about OO. What is OO? That's easy, you say. Object orientation. But what does that actually mean? Now, I thought it might be quite instructive to find out what you think it means. So I'm going to drop out of here again and go to the next slide. I think I can do that. There we go. If you go back to that same URL, if you're still there, you should be able to just enter words or short phrases that capture what you think object orientation means or things that are associated with object orientation. And it should start to build a word cloud. Now, not seeing any come up yet. Oh, there's one. Polymorphism. Great. There we go. Starting to get a few. Now, you can enter more than one word. So once you've entered one, you can go back and enter another one. You can even enter the same one, but don't use that to cheat. There we go. Encapsulation coming up pretty big. Got classes there, inheritance, all the usual suspects. Yeah, that's pretty good. Again, pretty much as I expected, but it's always nice to see when it actually goes as you expected. I'll give it a moment to settle down. Bugs, I like that one. Dynamic dispatch, that's interesting. Okay. If I remember, we'll come back to this at the end and compare notes. As I say, you can keep going. I'm going to carry on with the slides. So, all right. Part of the point of this exercise was that actually we do have different ideas about what object orientation really is. And if you do some reading online, you'll find different definitions, including from some authorities, so we'll have different ideas. But there are some common themes that most people agree. These are the core concepts of OO. But I thought it'd be useful to actually go back to where it all started. And most people agree that the first, what we would consider OO language, although some concepts had existed before that, was similar. Interesting thing about similar is that there were two similar languages, and they're actually both quite different. There was the original Similar 1, which was originally intended to be just an extension or a plugin to the Algol 60 language. Eventually, they realized that they couldn't do what they wanted to do just as an extension, and they had to write their own compiler, but it's still basically a superset of Algol 60. And they added a number of features. In fact, let's go on to have a look at that. Their main concept that they came up with was what they called a process, which itself was a generalization of a couple of concepts they'd had before that. And a process was really just like a function, or you might think like a function object that has just one member, one method, a run method. So you start the process and it starts running, but you can also suspend and resume it. You call other processes, you suspend yourself and you resume another process. So actually, you can think of these as a bit like coroutines. Now, this is not what we normally think of when we talk of Similar being the first object-oriented language. But it's actually quite interesting. This is where it actually started, this idea of processes. But when they came to do the next version of Similar, by that time, this had moved out of the research phase, and in fact, out of the simulation space. They realized they could make this much more general in application. And they wanted to generalize some of these concepts even more. And so they came up with something, well, it's actually already in existence before this, but they brought this into the language really for the first time in a mainstream language. And that was the class. And classes could inherit from other classes called subclassing, all sounding familiar now. And a class can have its own variables, member variables. It can have procedures that we now would call methods. And those procedures may be virtual. So yeah, this is all sounding much more familiar. And then you could have, say, certain types of classes. One special type of class was the process class. And this is how they actually got the old Similar 1 ideas into Similar 67. But they sort of brush them under the carpet a bit. Now, the new way forward with these classes. And in a way, it's a little bit of a shame that they de-emphasize that, because some of these ideas have come back to the forefront more recently, but actually we had them right there at the start in Similar 1. So we had virtuals, we had inheritance, so we had polymorphism. What it didn't have was encapsulation. Everything is basically public. Here's an example from there's a link at the bottom, 2bithistory.org. This will be in the references at the end. So I didn't come up with this example. I've never written a line of Similar, I should confess. But here we have a reasonably familiar example with a dog class, has a bark procedure. It's a little bit odd how you have to specify the virtuals. The comment suggests it's maybe something to do with GCC's implementation. GCC still has a Similar compiler front end, although it compiles down to C. So you can still play with this. And then you extend that with the Chihuahua class. Notice you put the parent class before the word class. So you have a dog class. Something nice about that. And then you can implement a new version of the bark procedure, which does something different. So fairly familiar the way that this polymorphism works. Very similar, other than the syntax, of course, but even that's not too far off C++ and other mainstream OO languages that we know. So once we moved to Similar 67, things started to get very familiar. But obviously things didn't stop there. There's a bit of a family history. So Similar itself belonged to the Algol family of languages. We already said that it started off as an extension to Algol. So very heavily borrowed the syntax of Algol. It's basically a superset. There was a whole other branch of the Algol line that led to the C language, CPL, BCPL, B, languages that you don't really hear anything of these days except as precursors to C. They didn't really have much impact beyond that, more iterative. And obviously they didn't go in the direction of OO. It is possible to do OO in those languages, but you have to work hard. The reason I bring that up is because, of course, we then have a common heritage in C++. So C++ lent heavily, of course, on C, but it got most of its OO ideas from similar. As we just saw, look very familiar in that sense. So that sort of algal loop reconvened in a sort of a virtual inheritance diamond of death at the bottom. But that wasn't the only direction that OO went in from similar. So a couple of other directions, very different directions, were Smalltalk and Eiffel, and both of them could be considered much purer implementations of the OO idea. So it can be instructive to look at what they do differently and whether that's better or worse or what the trade-offs are. Smalltalk's a particularly interesting branch because around the time that C++ was just getting going as an object-oriented extension to C, a lot of people were thinking, how can we make C object-oriented? That was the buzzword at the time. And one other application was to basically take Smalltalk and graft it on top of C and call it Objective-C. And when you think of the different directions that those languages came in at that point, it's actually remarkable just how cleanly Objective-C actually works. You can definitely see that the stratas of the language there, they're very different levels, much more so than in C++. But they actually complement each other quite nicely. There are some nice things about Objective-C. It's a shame, in a way, that that's been pushed aside in the favour of Swift these days. That's another story. But I think we lost something there. We certainly lost an enduring part of the Smalltalk legacy. But we'll come back to that anyway. Eiffel had some even stronger ideas about OO, as well as a number of other things that were starting to come round to thinking actually they're quite important, like contracts, for example. We're not going to talk quite so much about Eiffel. Obviously, this is a very simplified family tree. There are many other influences and influencers, different directions, but I think in terms of the OO story leading to C++, these are the main players. Even Objective-C had an influence in later times. So what I want to do is just take these languages, and I'm going to lump Smalltalk and Objective-C together for our purposes here, because in terms of OO, they're basically the same. And just compare the different OO features that they had, or have. So the first three are pretty common and pretty basic, fundamental. They all have classes, usually, I think always actually with the class keyword. They all support inheritance in some form, and they all support some form of polymorphism. I say some form, the differences in the details are actually quite interesting. We'll talk more about that. Inheritance, the main difference is similar and the Smalltalk line are purely single inheritance of both implementation and interface. Actually, Objective-C could have multiple interfaces called protocols. Whereas Eiffel and C++ support multiple inheritance. And it could be argued that actually Eiffel does a much better job of it than C++. I've considered many more of the edge cases that trouble us in C++ and done a better job of making those manageable. But then we start to get some more breakdowns. So as we said, similar didn't really support encapsulation. We didn't support it at all in the way that we know. There's no private keyword, no protected keyword. Everything is basically public. There was actually a very limited form of encapsulation. Remember that we said that Similar 1 had this idea of a process, which is like a coroutine. So a coroutine can have its own state, which would not be visible outside of the coroutine or the process. Now, whereas with a normal function, you wouldn't think anything more of that because these processes live on beyond invocations of other processes. You know, they run alongside them in a way. The fact that they have their own state, which is completely separate and encapsulated, it's actually quite an interesting idea. So I think we're going to come back to that as well. But in terms of the encapsulation that we know today, that didn't exist in Similar. That came about with Smalltalk and Eiffel. And then we have this idea that, well, if we're going to be object-oriented, then everything must be an object, including classes. Smalltalk went this direction, Eiffel went this direction, and many OO purists think that this is maybe the central idea in object orientation, that everything is an object. And certainly other mainstream languages, I mean, we're only considering up to C++ in this particular story, but thinking of languages like Java and C#, they don't have classes as objects, unless you consider reflection. But everything being a class is still there. So you can't just have free functions. They have to be wrapped in some class, even if they become static methods. And we may find that gets in the way, but it comes back to this idea that if you're really going to be object-oriented, then everything should be an object, even classes. And that's certainly true in Smalltalk, IFL, and even Objective-C. That's not true in C++. And it wasn't really true in Simula either. So there's another fault line. But I think the particularly interesting one, and this sort of follows on from that, is the way that Smalltalk and IFL support message passing. Might ask, what is message passing? And maybe you know what message passing is, maybe you have an idea, maybe you're not quite sure how that fits into OO, maybe you think it's a high-level concept. So it'd be instructive to have a look at that. So let's consider virtual dispatch as we have it in C++ today. So you have some code that wants to call a method on a class, which happens to be a virtual method. So you have your object implementing the class, which has a number of methods. You want to call method 1. Now to do that, first of all, of course, that under the hood will pass the hidden this pointer. It's as if you'd passed it manually. It's just been written for you and hidden. And there's even proposals going through at the moment to, in some cases, make that visible again, because it turns out that hiding it actually causes some problems. But this is what we know today. And then there's also this v-table that we don't see at all. And that also has to be considered when looking up what the method is. So there's actually a few levels of indirection we have to go through to invoke the virtual method, free by most counts. So there's a bit of overhead there. And this is one of the reasons that certainly virtual dispatch, as well as any form of polymorphism, are often not moved away from in a lot of modern C++ code bases by default. Obviously, they still exist in large numbers, but the sort of the leading edge of thinking in C++ is moving away from that. That's partly what this talk is about. Whereas in a message passing system, like a Smalltalk or Objective-C, I'm less familiar with how it works in IFL, so I'm not going to try to illustrate it. You say I want to pass the method 1 message to the object. So that does literally that. It passes it straight to the object. The object then has an opportunity to do whatever it wants with it, but the default thing it does is to then call it one of its methods. And there's usually a default mapping, so the end result is very similar to what we'd expect with virtual dispatch. And again, at that point, there is a self parameter, but that's passed by the object to the method rather than by the caller. Then there's no v-table, because this is effectively dynamic binding, and it's late binding, which actually gives you a lot more flexibility because the object gets to look in as to what happens before calling a method. It doesn't have to call a method. It could call a different method, or you could replace which method it's meant to call. Lots of things you can do, and lots of possibilities. Not all of them good, but many of them very useful. So there must be an overhead to this over the virtual dispatch approach, which must be why C++ does it a different way. And it's true, there is an overhead. You always pay the cost of this lookup every time, which on the surface is like a string lookup. In practice, it's a bit more optimized than that. In fact, over the years, this whole process, at least in Objective-C, has been so heavily optimized that at least last time I looked at any comparison, they were claiming that it was about the same overhead as virtual dispatch in C++. Now, these things change with CPU architectures, compiler optimizations and things, and probably doesn't consider devirtualization and that sort of thing. So I'm not going to claim that's always the case. If anything, it's going to steer slightly more in the direction of more overhead. But it's about the same, and that's actually quite interesting. That maybe we are paying for many of the penalties of using virtual dispatch and not really getting the benefit. Anyway, let's stack up some of these points. So, as we said, message passing is a form of dynamic binding, very late binding. So that means we have a chance to do, well, method swizzling is certainly what they call it in Objective-C. I don't know if that's a more general term, where you can say, well, normally when you call method 1, it will call this, but this time I want you to call this. And that lets you actually change what objects can call. JavaScript is famous for being able to do this as well. Monkey patching, I think they call it there. You can also have runtime delegation patterns. And that means you can actually hook in different behaviors at runtime, depending on runtime conditions. And a great example, again, coming from the Objective-C world, when you construct a string object, depending on properties of that string, such as its length, whether it contains Unicode characters or whatever else that it can examine in its constructor, it will then select a different implementation to actually implement that string at runtime and just hook it in with no additional overhead once that hooking up has been done. That's actually quite powerful when you think about it that way. Because you can change these methods at runtime, it makes these things really easy to mock. You just say, well, when you call me on this method, I want this to happen. That's exactly what you can do with message passing. With virtual dispatch, though, there are some advantages. It may be more efficient. As I say, there are some caveats here. It may not actually be that much more efficient, and it does depend on a number of factors. It can also give you stronger type checking, which may or may not be a benefit. Benefits basically end there, really. So actually, the scoring is not looking that good. Virtual dispatch also doesn't require, but usually implies that your objects be heap allocated. And this is perhaps the biggest source of dismay, I suppose, that C++ programmers will have when considering using virtual dispatch to implement polymorphism. Having these heap allocated objects that then have to be memory managed and the cost of the heap allocation. So there are ways to mitigate that, of course, but by default, that's generally what it implies. Now, there are other ways to implement polymorphism as well as message passing and virtual dispatch. Type erasure is a particularly popular one right now, which may or may not be implemented in terms of virtual dispatch. It doesn't have to be. So I put an example here of the Dino library. There's also Dynamix. Eduardo Madrid has something as well, including his any callable type. There's a lot of interesting work going on the library side in C++ around type erasure right now. In other languages, Rust traits are a similar concept, as well as Swift protocols, which are a bit deceptive because on the surface they just look like implementation inheritance and virtual dispatch, but actually you can do all the same sorts of things that you can do with type erasure with them. I'm not quite sure how they're implemented behind the scenes, but they certainly have the desirable properties. So what is type erasure? Well, we could do a whole talk on type erasure. So I'm not going to do it justice, but I will say it's just a way of having a value type where the actual implementing type can vary dynamically. And then the forwarding mechanism for any calls you make on it is handled much more directly, more like that message passing hookup that we talked about before. There's different ways to do that, so I'm not going to do it justice giving that coverage now. So it tends to be non-intrusive, whereas with virtual dispatch, you have to implement virtual methods and then implement those virtual methods, and you have to say what your superclass is and all of those things which just reek of virtual methods and inheritance. We don't need to have any of that with type erasure. You generally get much higher performance as a result as well, partly because you don't need the heap allocation. That can be a big part, but also because you remove some of those levels of indirection in dereferencing pointers and things along the virtual dispatch route. And there may be more optimization opportunities as a result of that because the compiler is much closer to the thing being called. So there may be, because obviously compilers tend to be optimized for the code that we write, and a lot of code out there is written using virtual dispatch. It's optimizing for that, but it may be starting to pick up on this trend as well. For me, maybe the most valuable part, though, is that type erasure is compatible with value types. As I say, you tend to wrap these things with a value type that you can pass around as a value, even though its implementation is polymorphic. That was the thing that we were usually interested in, the implementation being polymorphic, but treat the whole thing as a value. There's a really good talk that I'll mention in a moment, which goes into that in a lot more depth. But one more thing I wanted to mention about type erasure is concept mapping. Concept mapping is where you can implement a call on the top level type using a different call on the erased type. So it's like a mapping between the outward facing concept and the inward facing concept. And this is exactly what Swift protocols lets you do, which is why I lump it in with the type erasure, because it basically lets you do the same thing. It's actually quite powerful, and although you can do it with virtual dispatch, it's much harder and more intrusive again. So there's a lot going for type erasure, but there's also other forms of polymorphism out there. Some types, which in C++ we have in the form of stood variant and stood optional. Again, these are library implementations, which would be much better if they were in the language, or certainly stood variant, but we have them. They generally require you to use things like stood visit, which is fine, but again, it's not as clean as it would be if it was in the language. So talking of that, again, there are proposals going through the process, which may help here. Pattern matching seems to be getting along quite nicely. I'm hoping that's still targeting 23. I don't know whether that's been derailed by the current situation around the world. A lot of things are slowed down. It's an ambitious proposal, but a lot of people are interested in getting pattern matching in the language. Pattern matching is a much cleaner and more direct way of doing what we do with stood visit plus a lot more. It's a way of working with variant types, as well as lots of other types, but particularly thinking right now of variant types as polymorphic types. So the idea here is that rather than types being related in a hierarchy, as they have to be with virtual dispatch, types can be entirely independent, but you can still treat them in a more homogeneous way, a bit like with type erasure. Pattern matching will really help there. And there's also another proposal for a language level variant. And I haven't been keeping up on whether that's been progressing or not. I know originally we were waiting for pattern matching to get through as a precursor to it, but it may be pushed through in parallel anyway. So I'm saying that's probably going to be 26 at the earliest. So there are some things coming for providing more forms of polymorphism in C++. We also have templates, more recently concepts, which you can also consider to be forms of polymorphism, albeit at compile time rather than runtime. My point here is that there are many different types of polymorphism, not just virtual dispatch, not just the ones which rely on inheritance, and not just the ones which we tend to associate with object orientation, which tend to be the message passed in a virtual dispatch. Polymorphism is a really valuable concept in its own right. And in fact, many of these approaches to polymorphism are actually more popular in functional programming languages. Rich Hickey, the creator of Clojure, he likes to talk about polymorphism a la carte. So, we don't force you to use one particular type of polymorphism. They have their own strengths and weaknesses. Pick the one that's right on this occasion. Make them all available. We're gradually getting there in C++, but we've still got a ways to go. And virtual dispatch is probably the worst of the trade-offs that we have at the moment. Interestingly, virtual dispatch is the only one that relies on inheritance. And if we don't need inheritance to implement polymorphism, and set aside interfaces as well, which you can treat separately as other languages like Java and C# do, what else do we actually need implementation inheritance for? There are cases for implementing chunks of behavior, and we often will call these mix-ins. Again, in Rust, we call these traits, or some other languages. Mix-ins, traits, these are different names for being able to compose lumps of behavior together in an object, but in a cleaner way than we do with inheritance. Inheritance has a lot of problems in that regard. In fact, inheritance is not essential for being an OO language. Visual Basic, the original one, not the .NET incarnation, never had inheritance, but was considered to be a reasonably pure implementation of the OO concepts. So we don't strictly need inheritance. Polymorphism is definitely not a pure OO concept. It's much more widely applicable and valuable, and there's lots of different ways to do it that aren't strictly OO. So what else do we have? Well, encapsulation, that's got to be the big thing. This has got to be the core concept in object orientation. But that original language, Simula, remember we said actually didn't have encapsulation at all, except for that very limited form in Simula 1, which is not the sort of encapsulation as we think of it today. So all members were public, and yet we consider it the original OO language. So even encapsulation is not an inherent property of OO. That doesn't mean it's not a particularly valuable one. I would still argue it's probably the most valuable property of object orientation, and one that we would certainly want to maintain. But I want to go back for a moment to that Dijkstra essay and that section that I highlighted before. I want to read a few choice bits from there again and see what you think now. So he said, our powers to visualize processes evolving in time are relatively poorly developed, and that we should try to shorten the conceptual gap between the static program and the dynamic process and make that correspondence as trivial as possible. Now, say he was talking about the path of the instruction pointer through your code, but I don't know if you get the same feeling that I did when I read this, that he could equally have been talking about mutable state, processes evolving in time, our powers to visualize them poorly developed, conceptual gap between the static program as written and the dynamic process as it runs. Well, these are all things that apply to mutable state. If you have a variable which is mutable, in order to know what its value is at any point in the program, you have to consider pretty much every other point in the program. Everything is entwined. So reasoning about that value becomes really, really hard. Whereas if it's constant, it's trivial. Just to put something concrete on that, let's actually consider an example. So here's our first real class. Just going to go with a very basic date class. The purpose here is not to be a great date implementation. It's just illustrative. But we have some state, some integers for year, month, and day. We have a constructor, which, as well as letting you set those values, will also do some checking on their ranges. Now, I've used asserts here. If you want to make this input validation, you'd probably use exceptions or some other technique to verify it. The point here is that there's some way that we are checking those ranges. And I've elided the more complex bits. Let's just imagine you've been very thorough and validated that this is actually a real date that represents a real date in history or the future. Which means you get this nice property of correct by construction. If you can construct one of these, then you know it's a valid date. You cannot construct an invalid date. That's a really nice property that we generally strive for in particularly our value types. And I think we would consider this a value type. So that's quite nice. We also have some getters, just to give you access to the year, month, and day. And they're fairly innocuous. We need those because we have made our state private. Why do we make it private? Because that's how we do encapsulation. But consider this. If we did make that public, then what would happen? Well, first of all, we could lose the getters, because now we can just access those members directly. So I'd probably change the names, get rid of that prefix. We could also use a struct instead of a class. I like to do that when everything is public. For me, that states the intention as well as losing a line of code. But downside, of course, is that invariant, that this is always a valid date, is no longer enforced. That's the main consequence, not the only consequence, but the main consequence of breaking encapsulation. Now, let's say, there are other things that we get from encapsulation, mostly that we can change our private implementation to something else without breaking callers. But in this case, we were providing getters anyway. And yes, you can compute getters, you can do mappings and things. They give you some protection, but in many cases, your classes really are just bags of data that people just want to get the specific bits out that are in there. When that's not the case, then absolutely, encapsulation will help you. But in many, many cases, it really is just like this. We just want the year, the month, and the date, and that's how they're held. So, of course, if we made them const, then we wouldn't have the problem of being able to construct invalid dates anymore. So this, first of all, is a nod to what Dijkstra asked us to do what we can to close the gap between our ability to reason about the code as written and the code as it's running, so that we get fewer surprises. And when we do that, suddenly we find that encapsulation isn't as important as it was before for all of these types. As I say, it doesn't completely remove it, of course. But for many types, you can actually make the state public. And that simplifies some things. There's other ways actually you can also do this. So if you were using polymorphism, then you may only need to see that state in a particular module, to use that in the general sense, not modules in C++20, but like a translation unit or a component. So only that module, maybe that translation unit, actually has access to that private state without actually using the private keyword, whereas other clients would only access it via an interface if you were going to go that route. So there is also other ways to achieve the same effect without the forms of encapsulation that we've been used to, with private, protected, public. So maybe we should also be asking, are classes the right unit for even expressing this in the first place? There are other languages that do implement access control, but at the module level, and they seem to be actually better for it. So yeah, another question to ask about encapsulation. But I do think that certainly that component level, whether you call it a module or something else, encapsulation, that's where it's really important. Protecting what's in your implementation of your component from the outside world. And that's where we start to get back to something like Simula 1's processes. If you think of that process as like a module, self-contained, running itself. A little bit like Erlang has a similar approach. You have components, processes, again, that can talk to each other, message passing again, but they have internal state that can mutate, but it's completely encapsulated from the outside world. And this is real encapsulation. So the encapsulation we have in C++ is actually a bit broken. There's all sorts of ways that we can subvert it. Even just inheriting from a class gives us access to its protected data, at least, which in a way breaks some forms of encapsulation. A class, members of a class have access to the private members of another instance of the same class. But that's not so with languages like Erlang. And I would imagine even Simula 1, although, as I said, I've never actually written a line of Simula, so I'm extrapolating there. Okay, so we were talking a bit about mutability a moment ago and how that can impact encapsulation. And we also tied it back to Dijkstra's comments on how we can reason about our code, even though he never actually used the word reason. But we can't completely eliminate mutability. We want to minimize it to the essential mutability, but without it at all, our programs wouldn't do much. Even Haskell has to introduce mutability the back door, but it is there. But you want to be able to express it at the right level. And for me, what I've been leaning towards over the years is for that mutability to be mostly expressed at the component level, but at the lower level, strive for immutability, by which I mean using value types as much as possible and package them together into components that express those ideas of encapsulation and potentially act as processes. Now, there's one interesting thought here, which is when we talk about value types and value types being immutable. But we have value types, at least in C++, that are not immutable. String is probably the best example of that. Std string, you can mutate it in place, but it's a value type. So what's going on there? Well, I would argue it shouldn't be that way. And a talk I did a few years ago, Functional C++ for Fun and Profit, again, links at the end. I talk about a lot of this stuff, but I do specifically talk about a string implementation, just in general, although it's based on a few string implementations I have written, which is an immutable string, but paired with another type, which is well, I call it a string builder. And in general, you can refer to these things as builders. Their purpose is entirely to be mutable, to construct a particular value. And once you've got that value is then unchanging, immutable. But the interesting thing with the string builder is, first of all, using move semantics, you can construct that string in a piece of memory, but then pass that memory off to your value type to take ownership of, sole ownership. So it can now be shared because it's immutable. In this implementation, I made it reference counted. Doesn't have to be, but it actually worked out pretty well. But then if you want to change it later, you could move it back into a string builder. And if that was the last copy of that string, then that memory would then be transferred back to a string builder. You could mutate it again safely in the string builder and then move it back into another immutable string. Now, the purpose of going into this is to show how you can make explicit exactly where the mutations are allowed to occur. Rather than it being potentially anywhere in your code, you can say, well, I know that from the moment I get this immutable string to any other place that I use it, it's the same string. But this little bit of code that I've got over here, that's where the mutability is going on. And that's where I need to make sure that I can completely reason through what's happening. So you scope the mutability to exactly where you need it. And that's something that we can do with pretty much any value type, but we rarely do because it just feels more convenient to just leave everything mutable all the time. It's a bad habit, and we've lost our ability to even see how we can't reason about that anymore. Once you start to see it, you can actually be quite shocked at how you were able to live with it before. So, as I said, I've not done that justice. Go and watch that talk. But another great talk, which I did reference earlier, so I'll give you the talk title now. Juan Pedro Puente. We've done a few talks on this subject. I'm particularly thinking of this one he did last year at this year at C++ on C, because he talks about the intersection of value-oriented design and object-oriented systems, which is sort of what we're talking about here. So I've come around to saying value-oriented design is really what you want to be doing at the lower level. Actually, Juanpe talks about doing it at higher levels. Obviously, you can push that, but also does connect in with object-oriented systems. So it's a great talk. Encourage you to watch that one and many of his other talks on similar topics, including persistent data structures and that sort of thing. In fact, this is really what I want to lead on to. Can we get the best of both worlds? I've talked about how, ideally, for me, I see the low-level design being about value types, high-level design, component types that certainly include encapsulation. They may include other aspects of object orientation. But how can we bridge these worlds, and how can we get the best of both of them or all of them? Because one of C++'s biggest strengths is that it is a multi-paradigm language. In the early days, it was thought of as an OO language because that was the new thing, that was the buzzword and what everyone wanted to get into. And it was its main delta over C at the time. But it's grown into so much more. And it's still pushing into new paradigms that take on a more and more functional design aspects, and value types are becoming a very important consideration in new features. It's been a really great generic programming environment, certainly since the first standard. Many paradigms are supported fairly well in C++. I think there are a few that are supported really well, maybe generic programming. But how can we bring these all together? Well, let's summarize. So as I say, at the low level, prefer immutable value types is my advice. In order to do that well, you need to really understand certain other features, such as persistent data structures. In order to treat containers as immutable value types, persistent data structures are the only reasonable way to do that. And once you understand them, you realize they solve a whole load of other problems as well. Hate to say it, but becoming at least familiar with what monadic operations are can be valuable. You don't have to understand all of the theory behind them, although that can be useful. But this is going to become more and more of a topic. It's not actually going away. We've started to get used to it. Builders, a bit of a simpler idea, actually very simple idea, which is the beauty of it. As I mentioned with the strings, they're all about controlling the mutability phase to exactly the scope that we need it in, and no more, which is really what we're trying to do here. We want to be able to make our code reasonable, as in able to reason about it. And if we can keep as much of our code immutable as possible, while still allowing that essential mutability in, that's a really big way that we're going to be able to do that. And builders are a really powerful way to do that, and a really simple concept. And then we have functionally composable algorithms. So we're going to talk about these in this talk, but they're definitely something that supports this idea of immutable value types. Ranges are coming in C++ 20. They're only going to get more powerful over time. And they are a gateway to a lot of other functional concepts as well. So do become familiar with those. But that's at the low level. At the high level, depends on your project, on your architecture, but very often components with encapsulated state are the way to go. So if you think of particularly persistent data structures, you may have a large container of objects, but that structure is immutable. It can't change. So in order to add something to it, you actually need to take a copy of it, a very cheap copy. This is what persistent data structures give you, with the new item in it. And the only thing that then changes is the new root. Something has to hold that new root. And that thing then itself is mutable. And there are concepts in the functional world that sort of formalize this a bit. You may hear about ref cells and things like that. But all you really need to think about is, like we did with builders, try to constrain the mutability to certain well-defined places. Having your state encapsulated at the component level means you've got one level where you keep all of your mutable hooks to the other parts of your code, which are then themselves immutable. It takes a little getting your head around the idea, but once it clicks, you think, yes, that's how it all works. And of course, yes, it's always more complicated than that in practice. And there are additional research into things like software transactional memory to try to capture the more general case. But you can actually get a long way with some of the simple ideas, even if it's not exhaustive. Maybe also consider things like active objects, coroutines for encapsulation. may not be something that we're familiar with thinking about. These are all ideas. So I seem to have come to the end of this talk a little bit early, I think. So thinking I may have missed something. There's the link that I mentioned to my website, levelofinteraction.com. If you can't remember that, I also have extra levelofinteraction.com, the redirects there, of course. And then /refs, where I keep all of my talk references, /oo-harmful.html. That will get you the links. I'll try and remember to paste that in the chat afterwards as well. Now, I would have had my laptop up and running to be able to look at any questions that you may have. Unfortunately, the battery died and it doesn't seem to be revived. So I've asked Kevin, my volunteer buddy here, to pop into the stream to read out any questions that we may have. So Kevin, are you there?
Yep. Can you hear me all right?
Right. I can. Hello.
Okay. So Scott asks, in terms of encapsulation, I see functions are to classes as stack frames are to objects. Functions are methods without the, quote, this friend extra parameter potentially ruining your day. Do you have any thoughts?
I like the potentially ruining your day part. What I don't like is the way around that you're thinking of them. I would rather think of methods as just functions that happen to have some idea about an object associated with them. And then functions are the pure concept, which I'm sure is what you were saying. But yeah, not sure that answers the question though. Was it a question?
And that's all that we have in the Q&A right now.
Okay. Then I'm going to wrap up here because I'm a little bit early. I may have some time to spend at a table if anybody wants to reach me. Otherwise, I'm going to be over in the JetBrains room in about 15 minutes or so for a demo there. You can always catch me there, or maybe tomorrow at the conference. Thank you very much for listening.